Hello everyone, we are on the second worksheet of chapter 15, which is on inferences of regression, population regression lines. And this particular section is on the inferences for the slope of the population regression line. All right. Now the first question says, explain why the predictor variable is useless as a predictor of the response variable if the slope of the population regression line is 0. So, when it says the slope of the population regression line is 0, that means beta sub 1, right? What is the form of the population regression line? It's going to be y equals beta sub 0 plus beta sub 1 times x, where beta sub 1 is the slope of the line. Now, think about it. When we have different lines, if it is a slanted line, all right, so let's say we have here, let's mark the positive x-axis with some x values 1, 2, 3, and 4. And then along the y-axis, let's also mark some values 1, 2, 3, 4, and so on. All right. What kind of line has a slope which will be 0? It will be a horizontal line, right? Horizontal lines have slopes of 0. Horizontal line would have b sub 1 equal to 0. And what does that mean as far as x is concerned? Let me take out another color here. Let's say a horizontal line. We have a horizontal line passing through a y value of 2, right? What can we see? Well, what can we say about the y values as we move along our x values? When x is 1, y is 2, right? When x is 1, y is a 2. When x is 2, y is a 2. When x is 3, y is still a 2. When x is 4, y is still a 2. All right, so what do we see here? Even though we are plugging in different values of x, it's not having any effect on the value of y. Y remains 2, whether you plug in 1 or 4 or 50 or 0, it'll always remain 2. And that will be the case in any horizontal line, right? Y will be whatever point the horizontal line will cross the y-axis at. So that means x does not have any effect on the value of y. And that's why it's considered to be useless. X is not a good predictor of y. It doesn't predict y at all. No matter what value you plug in for x, the y value will stay unchanged, right? So let's look at this question here. It says, explain why the predictor variable, now predictor variable is the x variable, why the x variable is useless as a predictor of the response variable, which is the y variable, if the slope of the population regression line is 0. Now I have the answer written out here, so I'm going to read it aloud and explain a little bit. It says, if the slope of the population regression line is 0, that means if beta sub 1 equal to 0, then the conditional distribution of the response variable is still a normal distribution, but look at the mean. It will have a mean of beta sub 0 plus beta sub 1 times x. And if we plug in 0, this 0 in for the slope, what will we end up with? This whole term will become a 0, correct? And we will be left with whatever value beta sub 0 is. So beta sub 0 plus 0 times x is going to be equal to beta sub 0. And it'll have its standard deviation. Again, because we are talking about the population regression line, we use the sigma, the population standard deviation. And neither of these parameters involve x, right? Because x is 0. So we are left with an equation which is y equal to beta sub 0. This whole second term with the slope is eliminated. All right? And that is the reason x is useless as a predictor of y. Right? So that's the explanation. All right? So you have to kind of write somehow in your own words, possibly, that when beta sub 1 is equal to 0, when the slope is 0, then this x term is completely eliminated. No matter what you plug in for x, the y value will always be whatever beta sub 0 is. And therefore, x will not have any effect on the value of y, and that's why it is a useless predictor of the y or the response variable. Now question number 2 says, consider the standardized variable. Just a second, let me pull up my cursor here. Consider the standardized variable z equals beta sub 1 minus, let me say it again, sorry about that. Z equals b sub 1 minus beta sub 1. So b sub 1 is the slope of the sample regression line, and beta sub 1 is the slope of whatever the population regression line is, divided by sigma over square root over s sub xx. Now, whenever there is a z, there should be the population standard deviation. It should not be the sample standard deviation, because if it is a sample standard deviation, it will no longer be a z, it will become a t distribution. All right. So since they have a z here, that means it's going to be a standardized variable with a normal distribution. So the question here is, identify its distribution. Its distribution is going to be normal, because all z distributions, no matter what the formula is, associated formula is, will always be normal. Now, part B says, why can't it be used as the test statistic for a hypothesis test concerning beta sub 1? Because in most cases, sigma will be unknown. We've learned this before, started from the very first chapter that started inferential studies. Remember, confidence intervals. Whenever we do not have information on the population standard deviation, we cannot use sigma in our formula, and therefore we have to work with the sample standard deviation, and in that case we will need to use the t distribution. So to the question, why can't it be used as the test statistic? Because sigma is unknown. All right, sigma is unknown, and therefore z cannot be calculated. So what statistic is used and what is its distribution? We have to use our sample standard deviation, and the distribution that we will use is the t distribution. So our formula is going to look like this: b sub 1 minus beta sub 1 divided by s sub e, the standard error of estimate, divided by square root over s sub xx. So that's the formula that we are going to use when performing hypothesis tests on the slope it has to be a t distribution that we will be using. All right. So it's going to be a t distribution, but with all t distributions, we will always have a df associated, t distribution with df, and the formula for df in single variable, or rather in all regression testing or regression analysis, is going to be df equals n minus 2, because y minus 2, because we are working with two variables, all right, x and y. Now for the third question in this worksheet, I have the problem already worked out, so I'm just going to explain it. The question uses that same simple set of data that we have been using so far for this chapter. These three quantities for x and y, 2, 3, 4, 5, and 3, 6. 3, 7. And the question says, for the sample data and regression equation below, decide at the 10% significance level whether the data provides sufficient evidence to conclude that x is useful for predicting y. All right, so this is the data given to us, and associated with it, we are also given the regression equation, the sample regression equation, y hat equals 2 plus x. So we have to perform a hypothesis test on the slope. First step, state the hypothesis. And the way we state the hypothesis is null hypothesis H sub 0 colon B beta sub 1. All right, make sure again you are using the population slope notation. Beta sub 1 equal to 0. So the null hypothesis is always going to say that the x is not a useful predictor of y. That's what the null hypothesis is going to assert. The alternate hypothesis always states beta sub 1 is not equal to 0. It does not say whether it's less than or greater than. All right, that part will be done later on. We learn about that a little later when we do inferential studies on the correlation coefficient. All right, but when we are doing inferences on just the slope, the alternate hypothesis is always not equal to. So don't think whether it should be left-tailed or right-tailed. It's always not equal to, and therefore it's going to be a two-tailed test. All right. Step 2 is to determine the significance level alpha. Alpha is derived from our 10% significance level given in the question. So just change that to decimal. It's 0.10. And because the alternate hypothesis is not equal to, therefore becomes a two-tailed test. All right, and whenever we have a two-tailed test, we have to divide our alpha by 2, because a two-tailed test has reject regions on both sides of the curve, right? So we had to do alpha by 2, and we got 0.05. So now we are done with the first two steps. For step 3, we have to calculate our test statistic t, right? Our test statistic is our evidence that we take to the table when deciding whether the null hypothesis should be rejected or not rejected. So this is the formula for the t value that we have to calculate. It's b sub 1. Now, previously we said the formula, all right, just a second, let me pull up my pen again. Remember, we said the t formula, let me write it on this side, t equals b sub 1 minus beta sub 1 divided by s sub e over square root over s sub xx. Now, in this formula, however, we just have b sub 1. Why so? Because look at our null hypothesis. Our null hypothesis says beta sub 1 equal to 0. So we could have used this equation all right. It would be perfectly all right if you use this one instead of this one. However, because beta sub 1 equals 0, we would end up with b sub 1. B sub 1 minus 0 is b sub 1, right? So we would anyhow, or in any case, get to this equation, which is b sub 1 divided by s sub e over square root over s sub xx. All right, so that's the reason you don't see the minus beta sub 1 in this formula, when we had learned previously that this is the formula for the t statistic. All right, so now we have to find b sub 1. We have to plug in all these values, but before that we have to perform some calculations to find s sub e and s sub xx. Now s sub e we had actually found previously in 5.1, so I may just use that value. It was 2.449. I'm not recalculating it, but if you recall, s sub e was s sub xx divided by n minus 2 and the square root. All right, the square root over s sub, no, I'm sorry, it was s sub yy. Let's see, I don't want to misstate it. Give me a minute, please. SSE. It was SSE, all right? Excuse me, let me just correct it and write it here. All right. All right, S sub E was SSE. The formula for S sub E that we used previously was SSE, and then the square root divided by n minus 2. That was the formula we had used. So you may look up the previous worksheet on section 1 of chapter 15 to find out how we did the calculation. And we got a value of 2.449. So we are going to just reuse that value. I'm not going to recalculate it. But if over here, I have shown the work. All right. The formula for SSE is y minus y hat squared. All right. And then the sum of it. And there should be a square here. All right, y minus y. So just go through this process. If you need an explanation of this, please refer back to the solutions for 15.1. All right, for the first section of this chapter. Now, we need to know what s sub xx is. Now, s sub xx can be calculated using the either the defining formula or the computing formula. Again, I always think that the computing formula is way faster than the defining formula. So it's sigma x squared minus sigma x whole squared divided by n. All right, so what I did here was I listed my x values 2, 4, 3, and then I squared them in the next column. 2 squared is 4, 4 squared is 16, 3 squared is 9. I summed them up and I got my sigma x squared value of 29. And for the x, I just summed up all my x values, 2 plus 4 plus 3, 9. And that's going to be my sigma x. And then I plugged it into this equation here. Sigma x squared is 29. And minus sigma x whole squared, which is sigma x. I just plugged in 9 for sigma x and then squared it, divided by 3. So 9 squared divided by 3 is 27. 81 divided by 3 is 27. And 29 minus 27 is a 2. And that's the value of s sub xx. All right. So I have my s sub xx value, I have my s sub e value. So all we need to do is plug it into this formula here. So it's going to be 1 divided by 2.449. So the work is done here, all right? And let me just highlight it here, the calculation. So 1 divided by S sub E, which is 2.449, divided by square root over 2, we get a T sub 0 value of, or the test statistic value of 0.577. All right, so that's our test statistic, step 3 completed. Now I'm going to just use the critical value approach here and leave the p-value approach for you to work on. But for the p-value approach, remember, you just have to find the area corresponding to the test statistic value of 0.577, and you have to double it because it's a two-tailed test. All right, but let's go through the critical value approach first. So we have to define, in the critical value approach, we have to define our reject and do not reject regions. Because this is a two-tailed test, we have reject regions on both ends of the curve and the do not reject region in the middle, and each side has an area of alpha by 2. Let me fix this. It should be alpha by 2 and not alpha. So alpha by 2 on the right hand side is 0.05, on the left hand side is also 0.05. However, on the left hand side, the t value will be negative, then on the right hand side it will be positive. All right, so we are finding negative t of 0.05 with df equals 1. The df calculated using the formula n minus 2. All right, so let me write the CV here. The critical value is plus minus t of 0.05 with df equals 1, which comes to a value, so CV critical value is plus minus 6.314, and that's what we have here in the diagram. Now we bring our test statistic value, which is 0.577, and we have to show it somewhere in our diagram as well to demonstrate in which region it falls. So if this is the center point, then 0.577 is slightly to the right of 0, right? It'll be somewhere, maybe here. All right, so 0.577, so it clearly falls in the do not reject region. All right, so we've written here, since test statistic t sub 0 of 0.577 falls. Now let me correct this and make this a little more clear. This is confusing. Just a second. Since test statistic t sub 0 of 0.577 is, and you can demonstrate it like this, negative 6.314 less than 0.577 less than 6.314, which tells that 0.577 falls somewhere between the two cutoff points, right? So it falls in the do not reject region. Therefore, we do not reject the null hypothesis. And in the interpretation, we write, at the 10% significance level, there is not enough evidence to conclude that X is a useful predictor of Y. Right now, I'm going to go back a little bit to the p-value approach. I'm not going to give you the p-value because I expect you to estimate it using the table or using your graphing calculator. But let me again reiterate the process of finding the p-value. You have to take your test statistic value. So find area on one side of the test statistic value. Test statistic value, which in our case is t sub 0 equals 0.577 with DF equals 1, all right? And then you have to double it for two-tail tests, all right? Double the p-value, and then you compare 2 times p. And just because it's a two-tail test, we have to double the p-value, all right? If it were a one-tail test, you wouldn't have to do that. And then compare 2p with alpha. So if p is less than alpha, then reject, otherwise do not reject. Okay, otherwise do not reject. So that's the process. Do not reject. Now towards the later stage of this course, I do give students an option to use either the critical value or the p-value approach. So if you think that you're not comfortable with the p-value approach in estimating from the table, especially because the table will not give you an exact value, you will have to use some estimation, a p-value that falls between this value and that value, between two values, or less than or greater than. If you feel you're not too comfortable, just go with the critical value approach, all right? Because for the critical value approach, you will get the exact critical values from the table, right? So that's how we perform the hypothesis test. The next part of this question says, find a 90% confidence interval for the slope of the population regression line. All right, so 90%, and I'm going to erase some of the stuff which looks confusing. Okay. All right, so the steps are given here. We are using a 90% confidence interval. So our alpha is going to be 0.10 obtained from 1 minus 0.9, correct? Obtained from 1 minus 0.90. Alpha is 0.10. Alpha by 2 is 0.05, because for all confidence interval problems, you have to divide your alpha by 2 because the interval stretches on both sides of the center point of the curve. So we came up with our t of alpha by 2 value with df1 as 6.314, which was the same as the cutoffs, the critical value that we found previously for our hypothesis test. And now we have to use the formula given here. All right, again, b sub 1, beta sub 1, this is not beta sub 1, sorry, b sub 1, which is the slope of the sample regression line, was a 1. So 1 plus minus 6.314 is our t of alpha by 2 we found here, times s sub b was 2.449, and then square root over 2, because s sub xx is 2, and when we do the calculation, we come up with a value, an interval stretching from negative 9.36 to 11.936, and this interval contains a 0. Therefore, beta sub 1 is likely to be 0. All right, or it's likely to, and that's the reason we did not reject our null hypothesis. So this is in sync with the decision we got from our hypothesis test. Now, one other thing I just wanted to mention before I end this video solution: how did we come up with b sub 1 value of 1? All right, from this equation over here, the sample regression equation was y hat equals 2 plus x. So you have to look up the sample regression equation and look for what the slope value is. Now this is just x, so when the term is x, you don't see a visible coefficient, that means it's 1, right? So beta b sub 1 in this case is a 1. That's how we got extracted the slope value to be 1. All right.